Welcome you all. Today I am going to deliver lecture 2 of module 7, which is on treatment of wastewater produced from distillery and dairy industry. So if we remember in the previous lecture we have covered about the different processes which are used for fermentation of alcohol in the distillery industry, the batch process and the continuous process. So under this we are going to cover the basic introduction on the wastewater generation from distillery industry, and then we will be also looking up on the various sources like spent waste, spent lease, the various types of waste streams which are generated from the distillery industry, and then we will be also looking upon the various physiochemical biological characteristics of the wastewater streams which are generated from the process. And finally, we are going to look upon the various alternatives which are proposed for the treatment of wastewater. And among this, the most commonly used process, that is diaphagic anaerobic treatment system, and the UASB and hybrid reactor configurations which are used for the treatment and disposal of the spent waste, that we will be describing into more details. And then on the bioenergy potential of the distillery effluent in our country. And finally, we will conclude upon the basic numerical problem based on the amount of energy which can be generated from the treatment of the wastewater, and also on different alternatives. So here if we see the basic introduction about the wastewater which is generated from the distillery industry. So as we know, this distillery industry produces alcohol by the way of fermentation and distillation of sugarcane molasses, which is basically the byproduct of sugar industry, and this generates huge amount of wastewater in the tune of about 15 to 20 liter of wastewater that will be generated out of 1 liter of alcohol produced. And mostly if we see, as we have seen, like two types of waste streams are mainly generated. There are a number of streams, but mostly we see upon the spent waste and spent lease, which are high strength wastewater generated from the industries. And if we see in terms of its characteristics, so we find that this contains very high concentration of dissolved solids, very acidic in pH, a colored effluent, and is classified as a high strength wastewater. And in terms of temperature, this is around 70 to 80 degrees centigrade temperature of the effluent, which is very hot, highly acidic. And in terms of color, if we see, that is having a dark brown color and contains high concentration of inorganic and organic materials. So high concentration of this organic matter is mainly responsible for high concentration of BOD and COD present in this wastewater. So let us see more details about the various streams, various sources where from the wastewater is generated. So we see mainly there are 4 types of sources and the wastewater which are generated. The first one, if we see, that is the spent waste, which is the very high strength wastewater, and then this is spent lease, which is generated from rectification column, whereas the spent waste that is generated from boiling column. And similarly, because this is a lot of water is used as a cooling water, so that gets condensed, and this condensed water is also produced as one of the waste stream, and then we have cooling water. So these are the major waste streams which are generated from distillery industry, and this is the flow diagram of the different sources where from the different types of waste streams are generated. So if we see, this is like pre-fermenters where fermentation process is carried out. So here what we do, basically we use this distillery molasses, and this molasses is fermented using the particular type of yeast culture. So here fermentation will be done, and then after fermentation we see this carbon dioxide is produced, and Finally, we will left with the fermented vase that will contain lot of fermented alcohol, and then this fermented liquid will be sent to the analyzer column where alcohol which is in dissolved form that will be separated from rest of the water. So this is done by heating the fermented vase at a temperature of around 70 to 80 degree, 90 degree centigrade depending upon the type of process we use. And here what happens basically, at this temperature the alcohol vapor goes up, and then this water vapors being highly dense compared to the alcohol vapor. So alcohol vapor floats, goes towards the top, and this water vapor gets settled down, and from here it is taken out in the form of spent vase along with the fermented vase, which is separated from rest of the alcohol. So from top, if we see this, both water vapor and alcohol vapor will be generated, and then this will be sent again to the rectification column where the alcohol vapors will be completely separated from the water. So this is done again by density separation technique. So water vapors, they will go down, and this alcohol vapors that will be taken out from the top of the column, and this basically produces rectified spirit, which is around containing more than 99%, 100% of the alcohol. So from this two columns, like one we say that is analyzer column, and then another column which we say rectification column, where separation of water and alcohol vapor is done. So from here this spent lees are generated. So these are the major waste streams which are generated from the distillery wastewater. So now if we see what are the characteristics of the spent vase and the spent lees which are generated from the fermentation process. So here if we see in terms of flow, if we see the flow of the spent vase, there are two processes. One is like batch process and another is biostill process. So this we also know that is a continuous process, whereas the batch process, the fermentation process is done into number of pre-fermenters, and then it is taken as to the main fermenter. So this process is carried out in batches, whereas this is biostill process, that is basically the continuous process. So here in terms of flow, if we see around 2 times of the spent vase is generated compared to the biostill process. In batch process, if we see, that is 14 to 15 liter of spent vase will be generated per liter of alcohol, whereas in biostill process this amount is around 50% reduced, so that is around 7 to 9 liter per liter of alcohol. And in terms of color, if we see, that is having the dark brown color, and the same color we will also see in the biostill process. And in terms of pH also, if we see the pH of the spent vase which is generated from the batch process, that is very highly acidic, having the pH range 3.7 to 4.5, whereas in the continuous process the pH of the spent vase which is generated, that is around 4 to 4.2. And in terms of organic matter, if we see BOD, COD, so COD here if we see in batch process, that is around 90,000 to 1,10,000. If we see its BOD, so it contains around 50% of the total COD, so that is around 45,000 to 50,000. Whereas in case of this biostill process, if we see, that contains the COD up to the 1,60,000 to 2,10,000, whereas in case of BOD, this concentration is around 70,000 to 1,10,000. And overall, if we see the two process, so here if we see BOD and COD concentration that is generated in biostill process, that is about 2 times than the BOD and COD concentration which is generated from the batch process. And in terms of total solids also, if we see, that contains around 90,000 to 1,10,000 of total solids in batch process, whereas In biosteel process also, if we see, that is around 2 times, that is 1,80,000 to 2,20,000. And similar is the case for volatile solids, that is 50,000 to 60,000 in case of batch process, whereas this concentration in biosteel process, that is around 60,000 to 80,000 milligram per liter. And in terms of inorganics, if we see, that contains a lot of chloride, sulfate, nitrogen, phosphorus, and potassium. So here if we see chloride and sulfate, that is around, chloride if we see, that is 5,000 to 6,000, whereas in this biosteel process again it is 2 times, that is 10,000 to 12,000 milligram per liter. In case of sulfate, this is relatively 4,000 to 8,000 milligram per liter, whereas in case of biosteel process relatively 2 times than the batch process, and found in the range of 8,000 to 10,000 milligram per liter. In terms of total nitrogen also, if we see, it contains 1,000 to 1,200 milligram per liter of nitrogen, whereas in case of this biosteel process, this concentration is very high, that is around 2,000 to 2,500 milligram per liter. And similar is the case for potassium. Here if we see that the concentration is 8,000 to 12,000 in case of batch process, whereas it is around 2 to 2.5 times in case of biosteel process. And similar is the case for phosphorus in batch process. This is very less, 200 to 300 milligram per liter, whereas in case of biosteel process this goes to 1,600 to 2,000 milligram per liter. So this is like, if we see overall, compare the characteristic of the spent wash which is generated from the batch process and also which is generated from the biosteel process, we'll see the biosteel process, though the quantity of waste water, that is spent wash, which is relatively 50% than it is generated in the batch process, but in terms of concentration, if we see, that is around 2 times of the concentration normally which is observed in case of batch process. So here let us see the another waste stream which is generated from rectification column, where this alcohol vapors, they are separated from rest of the water vapors. So here if we see pH range varying from 3.6 to 4.5, but its BOD and COD, that is not very high. COD, that is around 5,000 to 6,000 milligram per liter, and this BOD concentration goes around 200 to 300 milligram per liter. Similarly, if we see, that is in terms of dissolved solids, so here the dissolved solid, that is around 5,000 to 6,000 milligram per liter, but suspended solid concentration, that is very less, around 500 to 1,000 milligram per liter. So mostly the solids which are present, they are in the dissolved form compared to the suspended form. And similarly chloride also, if we see in this type of waste stream like spent lees, the concentration is very, very less, like 1/100th times than the chloride concentration found in the spent wash. So this is one of the weak stream compared to the spent wash which is generated from the distillery industry. And after going through the details about the wastewater characterization, we come to know that the spent wash, that is very high strength wastewater and contains various types of suspended and dissolved impurities. So a single treatment system basically is not efficient for the treatment of the wastewater, which is basically the spent wash from this industry. So a combination of the following process that is being used, combining the physiochemical treatment process, aerobic treatment process, anaerobic treatment process. Somewhere in the older days this composting process were also used, and this incineration process can also be used to totally dispose this entire spent wash, to incinerate this spent wash, and then finally this treated effluent can be used for land application because it contains a lot of nutrients like phosphorus, potassium, nitrogen. So this have another alternative for its land application. So these are the various alternatives or the techniques which are used in the distillery industries. But out of these various techniques, if we see, more than 70 to 75% of the distilleries which are operating in our country, they are employing the anaerobic digestion system followed by aerobic treatment in the form of activated sludge process. So that is the most adopted technology, and we will be going in more details of this technology which are used for disposal and treatment of the spent waste. So under physiochemical treatment techniques, mostly we see that is like physical separation of the yeast culture, then cooling of the wastewater, which is having a temperature around 70 to 80 degrees centigrade, through designing number of cooling ponds, designing the equalization tank for equalizing the flow and the concentration of the wastewater generated from the process, because some of the process they use number of batch process which generates intermittent wastewater. So equalization tank is always used, and then since the wastewater is basically acidic in nature, so in physiochemical treatment also involves its neutralization. So these are the physiochemical treatment process which are essential for as a pre-treatment process for the treatment of the spent waste. Then for reducing the organic strength from the wastewater, we can have aerobic system, we can have anaerobic system. So out of the two systems, if we see that the concentration of organic matter which are present in the spent waste, that is very, very high compared to the aerobic system. Anaerobic system becomes more promising. So here the anaerobic systems are used. So in anaerobic system, again there are number of configurations that we will be discussing about, and then it follows the aerobic treatment system where the rest of the BOD and COD which are not being degraded in anaerobic treatment system, so that is being degraded in aerobic treatment system, which follows the anaerobic treatment system. And then finally the wastewater can be also used for composting, and there are other alternatives like incineration and its land application. So one by one we will be discussing about all these alternatives in the coming slide. So here if we see what kind of physiochemical treatment system that are used, like the kind of pre-treatment system which is required, because first of all, if we see the high temperature of spent waste is generated, so it needs cooling down the temperature of the wastewater before it goes for main treatment process to the atmospheric temperature, so which is basically tolerable by the anaerobic consortia. So first of all, the number of cooling ponds are designed, so that function is to bring down the temperature of the spent waste generated from the process to the atmospheric temperature, and this is done by designing number of cooling ponds. And then the second step, what that is like mixing. So this mixing of the intermittent wastewater is to be done in a equalization tank. So this equalization tank basically dampens the shock load, which basically equalizes the strong variation in the flow and the characteristics of the wastewater generated from time to time from the industry. So there is a equalization cum neutralization tank that has to be designed for mixing and dampening the shock loading to the biological treatment systems, which are the major treatment system used for removal of organic matter present into the wastewater. And then if you see, that is neutralization process, as I said in the equalization tank, this neutralization is a very important step, because the wastewater which contains having the pH range varying from 3 to 4.5, so this has to bring down to the slightly alkaline range, most optimized pH, which is required for anaerobic treatment system, which is 7.7 in case of distillery spent waste. So lot of alkali addition has to be done in the equalization tank for neutralization of the spent waste, which is basically acidic in nature. And then finally, if we see the overall characteristics, so we will see there is a lot of imbalance in the CNP ratio. So they are going out of range than the tolerance limit which is required. CNP ratio like 300:10:1 for anaerobic treatment system. So this adjustment has to be done. So we have to have addition of additional nutrients which is required for treatment of the wastewater. Then let us talk about the more details about these treatment processes which are used. So first of all, let us see the USB reactor, how it looks like. So U indicates for upflow, A for anaerobic, S for sludge, and then B abbreviates for blanket. So this USB reactor, if we see the influent wastewater that is fed into the reactor from bottom of the system, this is a manifold system which equipped with number of outlets from where the wastewater which enters into the system first strikes at the bottom, and then the entire wastewater in the form of layer goes towards rise upwards inside the reactor, and immediately after this sludge the wastewater feeding system, there is a sludge blanket which consists of high concentration of microorganism anaerobic consortia. So here, as soon as this wastewater comes in contact with this anaerobic consortia, so anaerobic digestion of the wastewater or the organic matter takes place, and as a result of carbon dioxide and methane that is generated. So these gases they generate and they lift upwards, and from the top of this the biogas is taken out. And if we see in the middle of this system, there is a deflector beams are provided which basically facilitate the removal of the biomass which gets buoyant along with the biogas. So they strikes with these deflector beams here. So this sludge mass is separated, and the rest of the biogas that goes towards the top and gets out of the reactor through the outlet vent pipe which is given for collection of this biogas generated from the system. And then if we see, this is basically the gas liquid solid separator system. When this treated wastewater comes with this, so it separates out the rest of the biomass. So this biomass, after getting separated, they will settle back to the system, and the biogas that will go towards the top, and the treated effluent that comes out through this effluent weirs are provided at the top. So treated wastewater that will go out of the system, and at the top, if we see, this is the floating domes that is provided, so which facilitate the collection of biogas, and that is taken out of the system through the vent pipe. And inside this, if we see, these are the small dots which basically shows the sludge blanket. If we see this, the bottom portion, that is a concentrated sludge stream, so this is called as the sludge bed. Whereas when the biogas is entrapped within this biomass, they get dispersed into the inside the reactor in a larger area and form a sludge blanket zone here, which helps in further degradation of the organic matter present into the wastewater. So this is all about the USB system. And then if we see this anaerobic contact process, the another type of system, this is the old system where the spent waste is filled into the reactor, where it undergoes anaerobic digestion system. So it contains active zone where the mixing of the sludge with the spent waste, incoming spent waste, is carried out by the mixers, and then the digestion process generates lot of biogas. the biogas generated from this process that will be stored in this floating dome, and from here through the vent pipe it is taken out. In this process, if we see from the bottom, this whatever the sludge that will be taken out along with the wastewater, so this will go to the vacuum degasifier, where this sludge along with the wastewater that will be degasified. Then this entire content that goes to the settling tank, where this sludge will be settled out at the bottom, and this will be taken out. A part of this that has to be recycled into the reactor so as to maintain the proper F/m ratio inside the system. So sludge recirculation, and then the vacuum degasifier of the sludge makes the sludge more settleable in nature, and then the treated effluent that forms the top layer in the settling tank that is taken out of the outlet pipe as a treated effluent. So this is the reactor configuration which are used for anaerobic contact process. So here both sludge degasifiers are used, recycling of sludge is used, mixing is done, whereas in the USB system, if we see, the mixing is performed by the flow system, and the biogas generated that creates the turbulence within the system and carried out the entire mixing process. And then another type of the system which is used, that is anaerobic filter media. Here if we see, this is the filter media which is filled into a tank, and the wastewater that the influent spent was that is fed to the reactor from the bottom of the reactor. When it goes towards the top, it comes in contact with the filter media, which provides the surface for the growth of anaerobic consortia. So as soon as this spent was comes in contact with this microorganism, its anaerobic degradation takes place, and it again forms lot of biogas, and then the biogas that will be collected through this vent pipe which is given at the top of the system. So this, from here the biogas will be taken out, and the treated water which goes at the top that will be connected through this effluent weir system, and it will be taken out of the reactor. So a part of again this wastewater, which is treated wastewater, that is again recycled into the system in order to maintain again this F/m ratio in anaerobic filter media. So these are the basically various reactor configurations which are used in the treatment of distillery spent was, various alternatives. Then let us see the another reactor configuration, which is basically the diphagic anaerobic treatment system, which is used for treatment of spent was. So this is the flow diagram. If we see, raw spent was basically first of all is given physiochemical treatment, pre-treatment, like it has to be sent to the number of cooling ponds. So the temperature of the spent was which comes out of the fermentation column, that is around having 70 to 90 degrees centigrade. So in this cooling ponds, they are basically shallow tanks which are used for the cooling of the spent was, bringing down the temperature to its atmospheric temperature, and then the cooled spent was that is sent to this holding tank, also called as the equalization cum neutralization tank. So here all the wastewater that will be again mixed together, and the pH, as we know this tank, the pH of the spent was that is around acidic range. So here we have to add lime or alkali material in order to bring up the pH to slightly alkaline range. And from number of studies, it has been found that if we maintain the pH more than 7.7, so that is like the toxicity due to sulfide formation that takes place during the anaerobic digestion process can be greatly controlled, and we can have more efficiency of anaerobic treatment system. So here we try to maintain a pH of 7.7 to something 7.8. So here that is to be done by adding lot of lime and alkaline material as per the requirement of the process. Then this, if we see here, we have two process like diphagic system if we see. So this is like anaerobic digestion process. If we see the pathways of anaerobic degradation of the organic matter, so there is acidification and then the two major process, acidification and then the methanogenesis. So here the two process they are carried out in two different stages. So first of all, entire spent was that is taken into the USB reactor 1, which is called as the acidic reactor, where first stage of the anaerobic treatment of the spent was is carried out, and all the organic compounds which are present into the spent was that will be converted into various forms of acid like propionic acid, valeric acid, organic acid, acetic acid, and finally there are acetogenic bacteria which will convert all these acids into this acetic acid, and then this wastewater containing lot of acidic acids that will be sent to this two number of USB reactors which are in the parallel. So the wastewater coming from acidic reactor that will go to the methanogenic reactor. So USB 2 and USB 3, they are basically the methanogenic reactors which carry out a conversion of this entire acetic acid into methane and carbon dioxide. So this total biogas generated through these two reactors that will be taken out of the process, and it will be further purified and the methane will be separated from rest of the component and then can be used as a source of energy generation. And here if we see in these two process, whatever the recycled effluent which contains lot of sludge, so they has to be separated, and then a part of this recycled effluent that has to be again recycled into the holding tank for helping into the neutralization of the spent was which comes from the cooling pond. And then you see after this treatment, if we see about 60 to 70% of organic matters, they are removed on this diphagic anaerobic treatment of the spent was. But if we see the analyze the treated effluent, still there is around 25,000 to 30,000 milligram per liter of COD still remains after this entire anaerobic process. So this is again then here, since the aerobic process they cannot be used for very high concentration, so this is again diluted in a dilution tank so as to reduce its concentration to 5,000 to 10,000 milligram per liter. So here 1:1 dilution is carried out with the water, and then this diluted spent was is sent to the aeration tank 1, aeration tank 2, which are there in the series. So these aeration tanks, they will further undergo aerobic decomposition of organic matters which are not anaerobically digested and will carry out the digestion process, will convert into carbon dioxide. And as this aeration tanks, they are basically the activated sludge process, so it is always combined with the secondary settling tank which is used for removal of the suspended microorganism which comes out of the reactor along with the treated wastewater. So here secondary settling tank, the amount of the biomass which is present in the treated effluent that will be separated, and a part of this will be again recycled into this to maintain a proper F/M ratio. So similar process here also in aeration tank 2 is also carried out. A part of this treated effluent will be recycled here, and then after this if we see the treated effluent comes to final treatment, and finally treated wastewater will be taken out, will be characterized and will be looked upon to meet with the effluent discharge standards. So here if we see there we are using the two number of settling tanks, whatever the sludge which are separated that is further taken into the sludge digester, which is one of the treatment system used for treatment and digestion of the sludge, and then this digested sludge that will be taken out to the sludge drying bed, which basically acts as filter to remove out the water from rest of the sludge, and that is basically a kind of filter be designed, and then this digested sludge that can be then disposed of, which contains a lot of nutrient and can be used for agricultural application for enhancing the fertility of the sludge. And if we see bioenergy potential of the distillery effluent, so here if we see, that is the data for different states, starting from Andhra Pradesh, Assam, Bihar, Goa, different states. So this basically says how much capacity of the alcohol industry we have in different states, the number of the units, and then the how much wastewater spent was that is generated from different distilleries. And this column gives about the biogas potential of the distillery industry into different states, and these columns basically gives the total nitrogen and the nutrient value which is present, and then finally this is giving the amount of biomass in terms of tons. So this is the data that we can see there is a huge potential of this industry in terms of generation of bioenergy. So if we see all the distilleries which are used to carry out this anaerobic process, they used to generate the biogas. Then this biogas they used to remove the carbon dioxide and other impurities from the biogas, and this methane is separated, which is having a calorific value around 5,000 to 6,000 kilocalorie, and that can be used for generation of electricity. And many of the plants they have this energy generation facility out of this treatment process. So now we will take some numericals which will describe about bioenergy potential of the distillery industry. So here if we see in this numerical, what we see, a distillery of 30 KLD, 30 KLD means 30 kiloliter per day capacity that generates spent was at a rate of 15 liter per liter of alcohol. And if we see its BOD concentration is given, that is around 1,50,000 milligram per liter. And it is said that the spent was is treated in a USB reactor and generates lot of methane. And the methane yield from the system, if we see, that is given 0.35 meter cube of methane that will be generated per kg of BOD removed. And also given that assume this biogas contains 70% of the methane and rest is carbon dioxide, and this methane has a calorific value of 900 kilocalorie per meter cube. And if we also see, there is a biogas production rate that is given as 0.5 meter cube per kg of BOD removed. So these are the problem, and then using this data, how we can use this data for determination of the total biogas which will be produced, and then the how much methane will be generated, and then what will be the energy equivalent of the total methane which is generated from the treatment of spent was. So if we see, first of all, we have to determine the quantity of spent was that is generated. So we have seen there is a ratio that is given 15 liter of spent was that will be generated out of per liter of alcohol being produced. So here our capacity of distillery that is given as 30 KLD, it means 30,000 liter per day. So if 30 kiloliter is converted by multiplying with this 1000, and this ratio is multiplied in order to get the total quantity of spent was that is generated, which is around 4,50,000 liter per day. And then the second step, we need to calculate how much BOD is removed so as to get the total amount of methane that will be generated. So here we know how much spent was is generated and how much BOD that will be generated. So here if we multiply this, the concentration of BOD in the spent was that is given in 1,50,000 milligram per liter. So if we convert in terms of kg, so we have to divide by 10 raised to the power 6. So this is multiplied by 10 raised to the power minus 6, and then this is total amount of spent was which is generated, we calculated here in this step. And then if we see around 85% removal efficiency we are assuming here, so it will give us how much BOD that will be removed. So this 85% is basically the COD removal efficiency that we have presumed while doing this calculation. So these are the other data like plant capacity, and this is BOD concentration, this is methane yield, what is given here, that is the calorific value, and then this is biogas production rate. So after calculating how much BOD that is being removed per day, we can calculate by multiplying with the biogas production rate, that is 0.5 meter cube per kg of BOD removed, that is the biogas production rate. And if we multiply with the total amount of BOD which is removed, which we have determined in the second step, so we can find out how much total quantity of this biogas that will be generated. So once we have got this biogas, we can calculate how much methane that will be produced. So this is like BOD removal rate, and then this is methane generation rate. So if we multiply with this, so we will get this total amount of methane that can be produced, because the theoretical methane yield, that is 0.35 meter cube of methane per kg of BOD removed, and that gives us a value of 20,081.25 meter cube of methane per day that will be generated from this treatment process. And then finally we have been asked to calculate its energy equivalent. So we know the calorific value of methane. If we multiply with its generation rate, so we can calculate how much total energy we can generate out of this treatment. That is obtained 180.73 into 10 raised to the power 6 kilocalorie per day. So these are the references that we can use for this topic. So thank you very much.